So what we do today is to formulate the Raman scattering process as a consequence of the light-matter interaction. So already, this is the last slide of the yesterday's talk. So we succeeded in formulating electromagnetic wave. What is molecule and what is interaction, right? Okay, already we finished formulation. So now what we need to consider is the event when electromagnetic field meets molecule, and let's define this as time 0, and the interaction starts. After starting interaction and spending some time, then optical event occurs. And during this process, Raman scattering occurs. So we want to know how to formulate this process. Before the interaction, there is a Hamiltonian of the radiation, Hamiltonian of the molecule, that's all. And in the presence of interaction Hamiltonian, and the status of the molecule and light changes time by time as a function of time. So we consider what goes on here. Okay, it's the same. Where there is a radiation, where there is a molecule, there are Hamiltonian or HR radiation and HE. Okay, interaction occurs, then we need to consider H prime as an additional term. This is smaller than HE plus HR. So this is treated as a perturbation. And we formulate optical responses. For that purpose, we should consider what is the expression of interaction Hamiltonian a little bit more. So yesterday I showed that the interaction Hamiltonian mainly consists of two parts, including A, P, and A square. And to formulate Raman scattering, we should consider the contribution from AP term. So I explain this term mainly. So AP term contains A and P. P is a momentum operator, A is a vector potential A. Already we know what is the function form of the vector potential A. So let's substitute this equation into this part. Then we get H prime AP term, the first term, like this. Because A includes creation operator and annihilation operator, so H prime AP also includes A and A dagger. You know, A and A dagger affects number of photons in the radiation. So, as a consequence of the presence of the interaction Hamiltonian H prime AP, the number of photons can increase or decrease depending on the optical process. Applying H prime AP and the number of photons having the vector potential K and polarization gamma increases or decreases. So this is the effect of this term. Then the Raman scattering process, it starts, so the population is mainly in the initial state, and light illuminates this molecule. Then some molecule undergoes optical process, so-called Raman scattering, and the light having different wave number vector and polarization is generated. And this process is explained by considering the twice application of H'(AP). Okay, so we should understand this process as a two-step perturbation from initial to intermediate to final. So accordingly, this is the second order perturbation. Initial state, the wave function is expressed as a product of wave function indicating that of the molecule I and the status of the radiation by listing the number of photons. And final state is here. Wave function includes molecular wave function F final state and the number of photons. Something decreases 1, something increases 1. This is some photon disappear, new photon appear. So Raman process is expressed in this way. Okay. So what we need to do is to solve the second order perturbation. Starting point is the Hamiltonian without interaction, that is, in other words, steady state. Nothing happens by time. It's stable. So Hamiltonian consists of radiation and molecule part. So let's regard that we know the nth eigenfunction psi 0 n r. And this wave function is obtained by solving this equation. So we know how to describe the wave function in the steady state. So we already have a complete set. Then let's move to interaction part. In this case, the Hamiltonian should include also the interacting Hamiltonian, right? Then, because of this term, the status of the molecule or the wave function changes time by time. For this reason, we need to solve the time-dependent Schrödinger equation. Okay, so this is given by equation 50. And we can assume the solution of this time-dependent Schrödinger equation like this. For this, so in the first case, wave function is a function of the position vector r only. But now, this is time dependent. So the condition, so the status of the molecule becomes a function of the position vector r as well as the time t. And this wave function should be described by using psi 0 and r. Okay? And contribution of each wave function in the steady state should be summed up. And temporal dependence or significance of this wave function is expressed by using the coefficient, time-dependent coefficient, B and T. B and T indicates the contribution of this wave function at time t. So the contribution of each wave function as a solution of the steady state Schrödinger equation changes time by time. So if B is large, contribution of this wave function is large. If B is small. The contribution of this wave function is small. So it varies time by time. And I skip the details, but the Raman process is a second order perturbation. So by considering the second order perturbation, we get the expression of B as a function of time, like this. During the Raman scattering process, the molecule starts from the initial state, go to the intermediate state. It may be real or virtual. I don't care for now. But passing through N and reach to the final state. So the energy difference between this light and this light corresponds to the vibrational energy. So we get the information of molecular vibration from this by measuring the wavelengths and the energy difference between this light and this light. But anyway, the molecule moves from initial through intermediate and reaches to final state. The probability of the occurrence of this process is calculated by considering BFT. This parameter indicates the probability that the molecule exists in the state F at time t. And this is expressed in this way. Interaction Hamiltonian appears several times. The first term corresponds to the first order perturbation, result of the first order perturbation, and it corresponds to Rayleigh scattering. The Raman scattering comes from the second term. Okay? So the intermediate state N appears here and here. So as a consequence of interaction, the state I goes to N. And as a consequence of the second perturbation, the state N goes to F. This is Raman scattering process, and H prime appears twice. In particular, H prime AP appears twice. Okay? This is the description. So, again, the Raman scattering is a two-step transition from I to F, I to N, N to F, two-step transition by intermediate state N. And we can describe the initial and the final state by using the wave function of the molecule I and F, as well as that of the right list of the quantum number. And some light, quantum number of some light decreases 1, and the other light increases 1. So this is the scattering process. On the other hand, energy is given like this. Energy of the whole system, including molecule and light, is expressed by considering the energy of molecule EI at initial state. And energy of light, the product of the number of photons and unit energy, plus the number of photons and the unit energy. And for the simplicity, we focus on the change in the number of photons for these two parameters. So I introduce this function, others, So n h bar omega of other components, 1, 1 or 1, 2 or something, something. So let's focus on the number of photons of k gamma and k prime gamma prime. And other, let's ignore or sum up the other term as others. Then the initial state is the sum of the energy of the molecule plus energy of the light. Final state, something decreases 1, something increases 1, and energy is that of the final state. And how about the intermediate state? From this equation, it's possible to consider two pathways of the transition. So we should consider two intermediates, N1 and N2. And this, I explained AP contains a creation operator and annihilation operator. So it may increase the number of photons or decrease the number of photons. Anyway, in the final state, something decreases 1 and something increases 1, but there is no hint about the order of decreasing and increasing. In that sense, we should consider two intermediates. In the first intermediate, number of photon quantum number decreases 1, and so from initial to N1 state, quantum number decreases 1, and during the transition from N2 to F, the quantum number of the other part increases 1. So minus plus. This is first pathway. When we consider N2, we can think about the possibility that the first step from initial to N2, photon increases 1. Then during the transition from N2 to F, the other decreases 1. So here is a diagram of the first N1 state. In the first step, incident photon is consumed to drive the system from I to N. So the number of photons decreases. Then in the second step, as a consequence of the interaction, light is emitted. So the number of photons of the other part increases 1. But only considering the equation, it's possible to consider the second possibility. That is, in the first step from initial to N2, photon increases 1. Initial to N2, photon increases 1. That is, emission occurs. After that, second component decreases. Second component is incident light. So incident light compensates the number of photons. So photon emission occurs first, and then incident beam is used for the recovery. Actually, it's difficult to consider the energy state lower than initial state. So this is mathematical possibility. But anyway, we need to consider both possibilities when we consider the formulation. And this page lists many equations, but please catch the idea. For further consideration, we can use some useful relationships. First, there are two ideas. Please understand. First, for further derivation, we should understand two ideas. First is the so-called dipole approximation. Okay? We have considered that when molecules go across the electric field, the force occurs and the interaction Hamiltonian occurs. Okay? But let's think about the size of the molecule and light dimension. Eigenfunctions such as I or F or N belong to the molecule, and it describes the distribution of the electrons around molecule. So we can expect that size of wave function is nearly the same order with the size of the molecule, small. It's a function of the R or position vector, and size of the molecule is in the order of nanometer or 0.1 nanometer, small. On the other hand, we also consider the electromagnetic field. What is the wavelength? Green light 532 nanometer YAG laser, nearly 500 nanometer. Okay, so let's think about 10 to the second or 10 to the cubic nanometer. Then, in this case, the wave number vector, length of the wave number vector is equal to 2 pi over lambda. And this is in the order of 10 to the minus second to 10 to the minus third nanometer inverse. Okay, so here is a figure. Yesterday I explained electromagnetic field. Molecule passes and goes by and force occurs. But when we consider the reality, we should think about this figure. Molecule is in the order of nanometer. Electromagnetic field, one period is 500 nanometer, 100 times different. So when we focus on size of molecule, electromagnetic field should be almost constant, not such a curving. For this reason, so this consideration results in relationship Kr should be much smaller than the unity. Okay, K is nanometer. No, R is nanometer. K is minus 2 to minus 3 nanometer inverse. Kr should be much smaller than 1. Then what happens? Yes. Where was it? So later it appears. But when we consider the exponential function, exponential plus minus ikr, then kr is much smaller than 1. Then it's possible to expand in this way. As far as kr is small, it's a good approximation. And second and latter term becomes much smaller than the first term. So we can assume that exponential term is nearly equal to the unity. This is so-called dipole approximation. Dipole approximation. Okay, this relationship allows us to deliver equation. make the equation much simpler. This is the first idea. One more point is that we can convert a momentum operator to coordinate. Okay, so generally, the textbook of the quantum mechanics tells us that there is a commutation relation between the Hamiltonian and R coordinate R. That is minus I h bar m bar mi pi. Okay. Then let's use substitute pi in this integral f pi I. Pi can be substituted with this term multiplied by some coefficient. Okay? And IMI over h bar, this term can be separated into two terms. F h e r I minus f r h e I. Okay? It can be separated into two terms. And we know HEF is F or I are the eigenfunctions of the Hamiltonian of the molecule He. So HEF is substituted to energy EF wave function F. HEI is replaced with energy EI wave function I. Excuse me. Sorry. Then EF is a scalar quantity, so it comes to outside of the integral, and R remains. So these two terms are summed up into this term, and EF minus EI is picked up. You know that EF minus EI is the energy difference between initial and final state. And this is replaced with h bar omega k. So it's possible to replace momentum operator with expression containing coordinate R. So please understand the idea, and we use this convenient relationship for further derivation. Again, the Raman term BFT square contains a wave function of the final state, HAP term, intermediate state, AP term, initial state. And former part, latter part is calculated in this way. And at this stage, this integral contains momentum operator pi. Then it's time to apply this convenient relationship to replace momentum operator pi to coordinate R. So it's possible to replace P with R. Okay? Some coefficient newly appears here. And further, the coordinate R can be replaced with dipole moment m. You know, dipole moment m is defined as a sum of the charge of ice particles and coordinate of ice particles. And summing up, we can calculate the dipole moment. And you know, here is charge of the ice particle and coordinate of ice particle. It ER appear twice. So this part can be replaced with the momentum dipole moment operator m. Okay, so in summary, we want to derive the equal relationship further, and consideration is separately done for the numerator and denominator. And about the numerator, we can replace momentum operator with coordinate r, and coordinate r is written in terms of the dipole moment m. On the other hand, the denominator can be written in this way. In the first term, EI minus EN, and I explained there are two intermediate states, N1, N2. So EI minus N1, EI minus N2. Two possibilities should be considered. EI minus EN1 is EI minus EN1 correspond to energy difference between energy of molecule small ei minus small en and energy of light h bar omega. On the other hand, ei minus n2 correspond to ei minus small ei minus small en2 minus h bar omega k. And considering the energy conservation, energy difference between final and initial state is the energy difference between incident beam and scattered beam. So by considering this relationship, we can rewrite this term like this. But anyway, by considering these points, we can derive Raman scattering intensity in this way. Okay, I explained each point later, but anyway, it comes from AP term of H prime interaction Hamiltonian and momentum operator M is included here. M is introduced by replacing momentum to coordinate to dipole moment M. And dipole moment M appears as an inner product with the polarization vector EK gamma, EK prime, gamma prime, or the inner product with EK gamma. It appears here. And there are two terms because there are two intermediate states, N1 and N2. And Raman intensity has a finite value when energy of the incident light is not zero. And omega k indicates the angular frequency of the incident light. nk gamma that appears here indicates the average number of photons having k prime gamma prime. Okay, please note that k prime gamma prime is different from k gamma. Okay, k gamma and k prime gamma prime is different. K prime gamma prime indicates the wave number vector and polarization of the scattered light. K gamma is that of the incident beam. This is scattered light. So, nk gamma bar indicates average number of photons having k prime gamma prime. This is the number of photons of the scattered light. Ek gamma and Ek prime gamma prime are the unit vector of the electric field of the incident and scattered light. And again, MBA is the abbreviation of the integral of BMA. This is a so-called transition dipole moment from state A to state B. It's difficult to explain at once. This process contains the transition from I to N, N to F. So there are two transitions, I to N, N to F, right? Accordingly, the moment includes the transition moment from I to N, N to F, I to N, N to F. Okay? Just a moment. So the Raman scattering occurs Raman intensity has non-zero value when the transition moment from I to N, MNI, and the transition moment from N to F, MFN, are both non-zero. It should be allowed to transition. If this is forbidden transition, intensity does not appear. Okay? So, and this is in the case N is a real state. If there is virtual state, intermediate state N, then this is virtually non-zero. Okay, because it includes all the possibilities. And we need to consider one more point. That is the frame of the coordinate. In the previous formulation, there was a term, inner product term of the Ek gamma and MFI, for example. So this is the inner product of the electric field polarization vector and transition moment. Please note that electric field vector is usually defined in the laboratory. You know, there is an optical table. We set the laser. Okay, laser goes this direction. Let's define this is Z direction. And this is, let's define this polarization X, this polarization Y. We can set polarization in the laboratory, in this room. Okay, macroscopic coordinate or laboratory frame. Usually we indicate by large XYZ. On the other hand, a transition dipole moment MFI is calculated by taking account of the wave function of the molecule at the initial state, final state, and momentum operator. initial state, final state, momentum operator are all defined on the molecule. Okay? There is no reason to use laboratory frame to describe the x direction of Benden molecule. Okay? Always we set the x and y on this figure. So these parameters are defined in molecule fixed frame, not in the laboratory frame. So this is a small xyz. So I derived this equation and I explained it includes E inner product of the vector E and M, E and M, E and M, E and M. But we should know E and M are defined in the different framework. So somehow we need to consider the relationship between laboratory frame and molecule fixed frame. For that purpose, we introduce an angle theta between the vectors E and M, okay, in the laboratory frame. In the laboratory, this molecule may direct this direction or this direction, this direction. In the solution, I don't know this. Where is it? What is the direction of this benzene plane? It must be isotropic, randomly distributing. So I don't know, but anyway, we can define the angle theta between E and M. Then the inner product of vector E and M can be expressed by using cosine theta. E is a unit vector, polarization vector, so the length is 1. Only the direction is the problem. So by introducing theta, E disappears and only theta remains. And the expected value of the cosine square theta, average value of the cosine square theta is 1/3 in the case the molecule randomly distributes, in the case of isotropic distribution. So we can replace this equation, this term with this term. Then 1/3 appears twice. And MFI that is defined in the molecular fixed frame is used as it is in the laboratory frame because it already takes account of the spatial averaging. Okay, so MNI, is used as it is with the term of the spatial averaging, and Raman intensity is calculated from this equation. Okay, so here sigma and rho are introduced to indicate x, y, z in the molecule fixed frame. Okay, M is a vector quantity, so it includes 3 components, x, y, z, in the molecule fixed frame. So sigma and rho indicates x component, y component, z component, x, y, z. So 3 by 3. So this term contains 9 components. But anyway, this page explains how to take account of the difference of the framework, coordinate framework. So again, Raman scattering intensity is given by this equation. We can learn some features from this equation. First, Raman intensity depends on the force power of the scattered light, angular frequency of the scattered light. That is, shorter wavelength light is scattered more. Okay? Force power dependency is not negligible. So when we excite the Raman process with 1064 nanometer intensity, Raman intensity is quite small. When we excite with 266 nanometer UV light, then scattered intensity is very large. So if possible, it's easier to detect Raman scattering signal with shorter wavelength excitation. Second point, Raman intensity is in proportion to nk prime gamma prime bar plus 1. What are they? Again, k gamma prime, k prime gamma prime indicates the wave number, vector, and polarization of the scattered light. And the intensity, Raman intensity depends on the number of photons of the scattered light. What it means? By introducing the same light with Raman scattering besides the excitation wavelength, Raman signal increases more. This is so-called stimulated Raman scattering that is intensified when omega k prime is irradiated. So we can enhance Raman signal by separately prepare the same wavelength with Raman signal. This is so-called stimulated Raman scattering. Plus 1 corresponds to spontaneous Raman. Without preparing such a additional beam, Raman scattering occurs spontaneously. So this term corresponds to spontaneous Raman. This term is stimulated Raman. Third, intensity of the Raman scattering is not equal to 0 only when MFN and MNI are non-zero, as I explained previously. If one of the two is 0, scattering intensity is 0. One more thing, important feature. There is a denominator I minus n plus omega k, h bar omega k. The denominator of the first term diverges if n really exists and it satisfies this relationship. In other words, if the excitation wavelengths correspond to the energy difference between the initial and real state n, then denominator approaches to 0. It results in the infinite intensity of the Raman signal. This is so-called resonance Raman effect. Actually, we have no chance to detect infinitely intense signal. So based on this expression, if this is 0, intensity to infinite, but in the reality, some enhancement is observed. If the denominator is larger than 0 or large enough, it happens when the n is far from the excitation wavelength. Then this term is non-zero. In this case, it corresponds to non-resonance Raman scattering. Okay, so this equation tells us some interesting and important features of the Raman scattering process. Okay. Raman scattering process may be written in this way by introducing alpha. So it's the same if we substitute this expression into this part, it is identical with the previous page. So by introducing alpha, we can write Raman intensity in this way. And in this case, alpha is, this part is so-called Raman scattering tensor. This is also known as the Kramers-Heisenberg formula. Okay? And rho and sigma correspond to xyz, xyz. Totally 3 by 3. It explains 9 independent components. Actually, not independent, but 9 components. So this is the same form with the polarization tensor, polarizability tensor. So this is a form of the tensor, Raman scattering tensor. Okay. So this is another way of writing of the Raman scattering tensor, Raman scattering intensity. One more important note. I explained Raman intensities in proportion to the force power of the Raman scattering frequency. Okay, it's true. According to this equation, it's true. Raman intensity is in proportion to the force power. Okay, this is the intensity of the Raman scattering light. Please remember, in many cases, we record Raman scattering using CCD detector. That is an instrument to convert the photon energy to electron energy. So, CCD detector counts up the number of photons. In this case, we should consider the relationship between the light intensity and photon energy. Intensity is force power dependence, but considering this relationship, the number of photons in the Raman scattering becomes cubic dependence. Okay, intensity and number of photons is different, so please consider this relationship. Okay. It may be a time to finish. Okay, I'm talking about this term. I need to explain further consideration in a short time, maybe in 5 minutes. Okay, further consideration about Raman scattering. Okay. It's a good approximation to separate the total wave function of the molecule into the contribution from electronic part, vibrational part, and rotational part, right? So, we can consider the behavior of the electrons by focusing on this part, vibration by focusing on this part, rotation by focusing on this part. It's a good approximation. But there is a fact that when the molecule vibrates, it's clear that the distribution of electron is different between static configuration and moving one. Okay? That is, wave function of the electron at given coordinate q, charge q and coordinate 0, that is stopping structure, is not equal to the electronic wave function with the charge q with vibrating coordinate along q. So we need to consider this feature, the vibration dependence of the electronic wave function. In this case, we should consider other electronic states mix into static wave function. This is the idea so-called Hertzberg-Terra expansion. The wave function of the electrons at vibration coordinate vibrating along the vibration coordinate q is explained by as a sum of the static wave function plus additional term. Additional term consists of the coefficient, vibration coordinate, and wave function, and other wave functions at a static condition. So, electronic wave function during the vibration is expressed as the original one plus some additional wave functions. Okay? So it's a linear combination of the static wave functions. And coefficient depends on Q. Q means molecular vibration. Molecular vibration is not only one. For the polyatomic molecules, there are 3 and minus 6 kinds of molecular vibration. So the mixing nature depends on each vibration. But anyway, instead of expressing the wave function by considering the electronic wave function and vibration wave function, we should use electronic wave function with the mixing along with the vibration Q and vibration wave function. Then here is the Raman tensor I explained previously. And transition moment I n m in this case, intermediate m, previously it was n. I m m f, there are 2 steps, I m m f, okay? And I should be affected molecular vibration. M electronic wave function of M should also be affected by mixing of the wave function F also. So let's replace the electronic wave function of IMF with this form, Hertzberg-Terra expansion. Okay. Then only I show the result. This is so-called, so based on this consideration, we can show that Raman tensor can be separated, classified into 3 groups, A, B, C. This is so-called Albrecht's ABC terms. A term is different from B and C. A term consists of difficult. So, electronic wave function consists of the main part and the additional part. Additional part contains coordinate q. And by substituting Hertzberg-Terra expansion, we can classify it into three groups. A group consists only of the main part of the electronic wave function. So initial, intermediate, final belong to ground, excited, excited ground, ground, excited, excited ground. So main part gives the A term. On the other hand, B and C terms contain one mixing part, mixing term. So coefficient and coordinate q appears once. Coefficient and coordinate q appears once. They are B and C. It's clear. Electronic wave function is mostly explained by the original wave function. So this is the largest. So this is a leading term in the Raman scattering in most cases. It depends on the symmetry. But anyway, this is largest contribution. Mixing term, mixing wave function is rather small. So B and C are relatively small, smaller than A. Then what is the difference between B and C? The difference appears here. B contains the mixing coefficient of ES or SE. C term contains mixing coefficient between TGT or TG. Just a moment. Is it possible? How can I use this? Okay. Okay, so this is a ground state, and this is excited state. G and E correspond to ground and excited. And ground state cannot be pure ground state because of the mixing of the wave functions. Excited state cannot be a pure excited state because of the mixing of the wave functions. So, upper state, there are many upper state. S1, S2, S3. HAES indicates the mixing coefficient of these wave functions into E. On the other hand, HAGT indicates the mixing of these wave functions into G. Okay? Then it's obvious. Energy level is closer between E and S. And when it mixes into G, we call it T1, T2, T3 or something. But energy spacing between G and T is large. Okay? In that sense. HA-GTTG is smaller than HA-ESSE because of the denominator. Because the denominator is smaller in the case of EE minus ES than EG minus ET. So this mixing term is larger than this mixing term. So typically, A is the largest contribution. A has the largest contribution. B is the second largest contribution. And C is negligibly small in the most cases. So by introducing Hertzberg-Taylor expansion, we can classify the Raman tensor into three groups A, B, C. A is the main part, B is the part containing the mixing term between excited state and other electronic states. C is the terms containing the mixing coefficient between the ground and excited states. So A is the largest, B is medium, C is small. So this is the classification, so-called Albrecht's ABC terms. Okay. And, sorry, a few pages, probably two pages. And in the fifth day, I explained the Hyper-Raman spectroscopy. And this is similar to Raman scattering, but in this case, this is a third-order perturbation. So this is a two-photon excited scattering process. First perturbation, second perturbation, third perturbation. So this is third-order perturbation. And Raman tensor, Hyper-Raman tensor is given in this way. Okay, again, sigma rho is xyz in the molecular fixed frame. And the resonance condition is a little bit different from Raman scattering because it consists of two terms. When excitation, twice of the excitation beam matches with the energy spacing between I and N, initial and N state, two photon resonance reaches to the real state. Then Hyper-Raman scattering becomes huge. Also, energy difference between initial and first intermediate state matches with the excitation wavelength. Also, this term contributes to the resonance effect. So Hyper-Raman spectroscopy has two kinds of resonance condition. In this regard, it's different from Raman scattering. But in principle, this is very weak process. This is third-order perturbation, so it's difficult to detect. Advantage, unique selection rule, unique resonance condition. Drawback is it's weak. One photon out of 10 to 12 power photons. Okay. This is the last page. By substituting electronic wave function by following the Hertzberg-Taylor expansion, we can again separate the Hyper-Raman tensor into A, B, C. And A is the main part. B is the part that contains one coefficient or additional term. C term involves twice the additional term, and this is too small to discuss. So usually we discuss A contributions from A term and B term. And in most cases, A term is the most important, the most strongest. Okay. So this is all for today's my talk. It's 1 hour. Okay. So I explained how to formulate Raman scattering process and I explained mixing of the electronic wave function. And by considering the mixing of wave function, we can classify the Raman tensor into A group, B group, C group. And I introduced the expression of the hyperpolarizability, Hyper-Raman tensor. Okay, so this is all for this lecture. Okay. Sorry?
The N1 and N2 part.
N1 and N2 part. Okay. Raman scattering. This is related to Raman scattering process. So we need to consider two kinds of intermediate states. Okay. So in Raman scattering in this way. Okay, initial state is populated, light comes in and it excites the molecule into the intermediate state, and scattering occurs and new light is emitted. Okay, this is Raman scattering. And based on the formulation, it's possible, but if virtually, it's possible to consider another pathway. So in this case, one photon decreases first, then one photon increases next. But equally possible pathway is that one photon increases first, one photon decreases next, opposite order. So I don't say you must find such a negative energy state. I don't say. But according to this formulation, this is another possible pathway, and we cannot remove this possibility.
And sir, after some point, cos, there was a term where cos square theta was considered 1 by 3.
Sorry.
There was a term where cos square theta was considered 1 by 3.
You mean the spatial averaging? Here?
Yes.
So, as I explained, polarization of the laser beam is defined in the laboratory. Okay? We call this is x-axis, y-axis, z-axis. And on the other hand, molecule is defined in the molecular frame. We define this is xy plane and normal is z. There is no relationship between small xyz and large xyz. Okay? But somehow we need to obtain the inner product. Okay, then let's consider how to describe the direction of the small xyz in this frame. Then how can I erase this? I see. Yeah, thank you. Okay, so this is a laboratory frame x, y, z. Then there is another x, y, z. And these two coordinates can be this small xyz frame can be made set identical by considering three angles, so-called Eulian angle. So I cannot explain in this figure, but anyway, by considering some three angles, it's possible to make it identical. But anyway, here is the propagation direction light, and the electric field here E, or unit vector k gamma. Let's introduce. Let's EK gamma in laboratory frame. Then molecule directs this direction. So this is non-polar molecule. So instead of benzene, you may consider acetonitrile or something, polar molecule. Then, in this case, dipole moment mu, or in this case, transition moment mu m. This is vector quantity. And always we can define the angle theta between two vectors. Okay? Then cosine theta makes and by considering cosine theta, we can calculate the inner product. So cosine theta is introduced here. It's square, so cosine square theta is introduced here. And by integrating over all cosine theta, all angle theta, it becomes 1/3. So this is a spatial averaging. That's it. Okay.
Next.
Thank you. Yeah.
So, can you please explain to me what is the resonance Raman effect?
Okay. Resonance Raman effect. So here is the ground state, and molecule is here. And this is the intermediate state. So light has an energy h bar omega. Okay. So energy, the energy of light drives molecule to first intermediate state. And this is scattering process, so there is no real population, and immediately after reaching to the intermediate state, scattering light occurs. So this is Raman process. And this equation tells us that if the energy is identical to the energy spacing between ground and the intermediate real state, then denominator reaches to 0 or very small value. According to this formulation, Raman scattering becomes very strong. So this is a resonance effect, so-called resonance effect. So during these 5 days lecture, I will introduce some examples. But you know, myoglobin, here is a protein, and it contains heme. Protein part has absorption near 210 or short wavelengths. And aromatic phenylalanine, tyrosine, tryptophan. Aromatic groups has absorption near 280. And heme gives the absorption at 400 or 500 around this region, visible region. So these absorption indicates their real energy state. So by tuning the excitation wavelength to this absorption, or this absorption, or this absorption, the Raman signal of each chromophore is enhanced than the others. So this is a method to intensify the Raman signal from a particular chromophore that gives the absorption. Okay.
I want just two basic terms like spontaneous Raman and stimulated Raman. We are using these words. So could you explain it?
Stimulated Raman and spontaneous Raman. Okay. Okay. So different color. Okay, so here is a ground state and intermediate state, and excitation beam comes, scattering occurs. This is spontaneous Raman. And in this case, we put a sample, irradiate the beam, and scattering occurs everywhere. Okay? This is spontaneous Raman. On the other hand, here is a sample. Okay, irradiate the light. And Raman scattering occurs. We set one more light. So excitation is beam is specified by K gamma, and scattered light is K prime gamma prime, or depending on the direction, gamma prime, or having different wave number vector. And some component goes forward. So let's say K circle, gamma circle. By preparing K circle, gamma circle as an experimental setup, by introducing this light, this scattering becomes intensified. So by preparing some photons that correspond to the Raman scattering wavelengths, we can intensify the Raman signal. That is the simulated Raman. So this is quite different from spontaneous Raman. Spontaneous Raman occurs without any additional light. Only excitation beam is necessary. So it's a quite different experiment.
Among Raman and Hyper-Raman scattering, whose intensity is like dominative? And can you please discuss the factors of dominance?
It's quite difficult. You mean the difference in the contribution between A and B?
Among Raman and Hyper-Raman scattering, the difference in intensity, whose is dominant one among the both?
So Raman scattering is much stronger than Hyper-Raman.
Are there any factors of dominance?
Sorry?
Are there any factors like on the basis?
So the Raman scattering occurs as a consequence of the second order perturbation. So the interaction between light and molecule occurs twice. And in the case of Hyper-Raman, it occurs 3 times. The probability becomes much smaller. That's why Hyper-Raman scattering does not occur so frequently. So Hyper-Raman scattering is weak. And twice interaction occurs more than Hyper-Raman. So everyone says Raman scattering is very weak, so it's difficult to use. But for me, Hyper-Raman is much weaker, so Raman intensity is not so weak. Okay, is it good answer? Or okay. Mhm. So, virtual and real intermediate state. So, always we may use this figure. Okay. So, we consider everyone is in the initial state and passing through the intermediate state and go to final state. So, when we call intermediate state is virtual, then we are thinking about the contribution from all the electronic states that is far from excitation energy. So not only one state contribute to the intensity, all levels, but far from excitation. We call this kind of not unidentifiable states as a virtual state. If there is real energy state, then this is real state. So real state means some absorption occurs, absorption band is observed. Okay.
Can you tell more about
Hi.
the two-photon extraction process, that is Hyper-Raman spectroscopies? Can you separate more about the two-photon extraction?
Hyper-Raman process. Okay, two-photon excitation. So Hyper-Raman process is different from Raman process. So in the case of Raman process, one photon excitation and scattering occurs, but there is another event when we put a molecule in the electric magnetic field. So it's rare, but with a finite probability, third order perturbation occurs. And in this case, one process is that excitation occurs twice. So if this is 532, then excitation beam, Hyper-Raman signal is nearly 266. So nearly twice the energy. Exactly speaking, vibration energy is reduced from this, right? But so it's possible to observe such a process. This is a two-photon absorption. Okay.